Yeah, hello students. Now let us discuss about how to draw the shear force and bending moment diagram for a simply supported beam carrying UDL of intensity small w Newton per meter over the entire span. Now for that case, I'm considering a simply supported beam of span L. Now this simply supported beam is carrying a UDL uniformly distributed load of intensity small w over the entire span. Now as you know that the first thing what we need to do here is we have to calculate the support reactions. I'm calculating the support reactions. As there are no horizontal forces, I'm not going with sigma fx is equal to 0. Let us go with sigma forces acting in the vertical direction. It is equal to 0. So let us consider there is a reaction RA at A and a reaction RB at B, vertical reactions. So RA plus RB will be equal to the total load which is acting in the downward direction, that is W multiplied by L. Intensity of load will be W multiplied by L. So this is W into L. RA plus RB is equal to W into L. This is the first equation. Now let us take moment at point A. Sigma moment taken at point A is equal to 0. Now with respect to point A, there are two forces which are creating some moment. Let us go with RB first. RB multiplied by L will be the moment, but it is acting in the anti-clockwise direction. Anti-clockwise moment should be taken positive, plus RB multiplied by L. And W with respect to point A is creating a clockwise rotational effect. It is creating a clockwise rotational effect. So minus W multiplied by L is the intensity multiplied by L by 2. So it will be acting exactly distance of L by 2. So I'll take this one as L by 2 is equal to 0. Now RB is equal to W L square divided by 2 multiplied by 1 by L. So we'll get WL divided by 2. So when RB is equal to WL divided by 2, I'm substituting the same thing in equation number 1. We get RA is equal to WL divided by 2. We got both the reactions RA and RB. So RA it is equal to WL by 2 and RB it is equal to WL divided by 2. WL by 2 and WL by 2. Now in order to calculate the shear force, I'm just considering a section X and X, or capital X and X, which is located exactly at a distance of small x from point B. From point B, shear force. Now shear force at any section X and X, I'm considering right side portion of the section. Towards right side of the section we have two forces here. One is RB, the other one is the UDL. So right side downwards should be taken as positive, right side upward should be taken as negative. Now shear force at any section XX will be equal to, it is simply algebraic sum of all the unbalanced forces towards the left or right side of the section. So this will be W multiplied by X. The intensity of load which is acting towards right side of section, UDL, for UDL it will be W multiplied by X. So this is plus W multiplied by X, and RB, right, which is minus WL divided by 2. WL divided by 2. Now calculating the shear force here, shear force at X is equal to 0. That means shear force at point B. Shear force at point B. Now this will be equal to W multiplied by 0 minus WL divided by 2. So that is minus WL divided by 2. So shear force at point B is equal to minus WL divided by 2. So this is negative. Why negative? Because it is acting in the upward direction. So right side upward should be taken as negative. So what do you understand from this one? Shear force at point B, it is equal to WL divided by 2. What do you understand from this one? For any simply supported beam, shear force at the supports will be equal to support reaction only. Remember this one. Shear force at any support will be equal to support reaction. Right. The same thing again. I can see with the rule which I have explained just now. I can directly write shear force at point A will be equal to WL by 2 again. WL by 2. But it is positive. Why it should be positive? Why it should be positive? Because see, the same section I am considering, towards left side of the section, a force is acting in the upward direction. Force is acting in the upward direction. When it is acting in the upward direction, what will happen? Towards left side of the section, it is acting in the upward direction. According to sign convention which I gave you, this has to be positive. Right? Right side downwards, positive. Left side upwards, positive. So this is positive value. Right? So we got two values here. Now, how will be the variation in between these two things? So shear force at A and shear force at B, both the values are known to us, and there is only one UDL which is acting in between. Now, just look at the screen, everyone. Just I'll tell you how to draw the shear force diagram. I have drawn the baseline, right? This is shear force diagram, SFD. I have drawn the baseline here. Exactly at point B, we have minus WL by 2. Minus WL by 2 should be plotted in the downward direction. This is minus WL by 2. And exactly at point A, it is plus WL by 2. Right? No need to indicate plus and minus, because below the baseline, it is negative. Above the baseline, it should be positive. Right? Now, simply draw a straight line which is joining both the values of shear force at point B and at point A. This is WL by 2 and this one is WL by 2. Now here this portion will be positive and this portion will be negative. Now exactly at a particular point, the shear force is equal to 0. Now if I want to determine which point the shear force is 0, shear force is equal to 0. Right? See, I have generated one equation here. Shear force at any section X will be equal to W into X minus WL by 2. Right? I will equate this particular equation to 0. Right? That's it. Plus W into X minus WL by 2 is equal to 0. It is equal to 0. Now, W into X is equal to WL by 2. Now, X will be equal to L by 2. Simply. Now, at a distance of X is equal to L by 2, shear force will be equal to 0. At a distance of X is equal to L by 2, shear force is equal to 0. That means at what distance it is equal to 0? L by 2. Exactly at distance of L by 2, shear force is equal to 0. Now, for the same simply supported beam, let us calculate the bending moments and draw the bending moment diagram. For that thing, I need to draw the separate sketch again. Now, here you can see I have drawn the shear force diagram once again. So this is the shear force diagram. Now, to calculate the bending moments, to calculate the bending moments, what I'm doing here is just same thing again. I'm just considering a section X and X. Now this section is located exactly distance of small x from point B. As we know that the entire span, right, it is L. Now this section is located exactly distance of small x from point B. Now the intensity of loading is W Newton per meter. Now bending moment at any section X and X will be equal to, so I'm considering right side of the section. You can also consider left side of section. It is up to you, right? For my convenience, I'm just considering right side of the section. Now, towards right side of the section, how many forces do we see here? One is WL by 2. The first force is WL by 2, which is acting in the upward direction. The next one is W Newton per meter, UDL, which is acting in the downward direction. Now, this force WL by 2 is trying to push the beam in the upward direction. That means it will try to bend in the upward direction. The beam will be trying to bending in the upward direction. That means it is creating some sagging moment. Now, the moment created by WL by 2 will be positive, whereas the UDL, W, which is acting over a span of X, will be trying to push the beam in the downward direction, which will create some hogging moment. Hence, for this load, W Newton per meter, the bending moment will be negative. For this load WL by 2, it will be positive. So I'm going with WL by 2 first. So this is positive WL by 2 multiplied by X. Force multiplied by perpendicular distance. This is force and this one is perpendicular distance. Next, minus for UDL. This is for point load. And now I'm writing it for UDL. W multiplied by X is the intensity of load. W into X multiplied by, at what distance it will be acting? Exactly at the distance of X by 2 multiplied by X by 2. So this is equal to W L multiplied by x divided by 2 minus W x square divided by 2. Here you can see it is a second degree quadratic equation. Second degree equation. Hence the variation of the bending moment diagram will be parabola. Now my intention is to calculate bending moment at a distance of x is equal to 0. That means bending moment at point capital B. Right, so this will just substitute x is equal to 0. When I substitute x is equal to 0 in this equation, W into L multiplied by 0 is 0 minus W into 0 square divided by 2 is 0. So bending moment at point B will be equal to 0. And there is one simple thing you have to remember here, right? For any simply supported beam, bending moment at the support will be equal to 0. Next, same thing again. I want to calculate bending moment at x is equal to L by 2 at a distance of x is equal to L by 2. Same thing again, just substitute in place of x L by 2. WL by 2 multiplied by L by 2 minus W by 2 multiplied by L by 2 whole square. So what will it be now? W L square by 4 minus W L square by 4 to the 8. So this will be W L square by 8. We got a positive value here. L divided by whole square will be L square and 2 square will be 4. 4 2 is 8. So I have written the same thing here. So WL square by 8. Now if I take the center point of the beam as C, right, bending moment at a distance of x is equal to L by 2, or bending moment at point C will be equal to WL square by 8 plus value. Exactly at a distance of L by 2, mid portion. Same thing again, suppose if I take this one as WL by 2 point A and I am considering a section XX which is located at distance of x, right, a UDL. This is W Newton per meter. Now towards left side of section, just I am considering left side of the section, I'll generate a bending moment equation for your convenience, because in most of the cases I'll be taking towards right side of the equation, right side of the section. Now let me consider the left side of the section here. Bending moment at any section x and x will be equal to, see, this WL by 2 is trying to push the beam in the upward direction, will be creating some positive bending moment. So I'll take WL by 2 multiplied by x, force multiplied by perpendicular distance. Next, W Newton per meter is trying to bend the beam in the downward direction. It is trying to bend the beam in the downward direction. Hence, for this thing it will be negative. Minus W into x is the intensity of load multiplied by x by 2 is the perpendicular distance. See, we got the same equation, WL into x divided by 2, right, minus WX into x by 2. Same thing again, bending moment at a distance of x is equal to 0. That means bending moment at point A, right, substitute x is equal to 0, you will get value 0. So bending moment at point A is equal to 0 again. Now let me draw the bending moment diagram, right. See, we got bending moment at point B is 0, bending moment at point A is 0, and bending moment at point C is WL square by 8. And the equation we obtained here is a quadratic equation, second degree equation. For second degree equation, for first degree equation, it should be a straight line. For second degree equation, it should be a parabola. You have to remember this one. And for cubic equation, for third degree, right, it should be cubic parabola. Cubic parabola, right. Now same thing again, just simply draw a baseline, and at point A bending moment is 0, at point B again the bending moment is 0, and exactly at point C we got the maximum bending moment, that is WL square by 8. So I am marking WL square by 8 over here. And the variation from point A to point C and point B, it will be a parabola. As you can see here, just I am drawing a curve which is simply indicating a parabolic curve like this. Parabolic curve, right? A simple curve. Now this is positive. And whatever the value which we get here, it is WL square by 8, positive value. So in this way, we have to draw the shear force and bending moment diagram. So this is shear force diagram, SFD, and this one is BMD. That's it. Thank you very much.